So good morning, everyone, and welcome to this lecture. This is lecture number 2 in Newton laws, and what we were discussing in the previous class. I think we were discussing the types of force, and we had seen the different types of forces and how they are classified. We had seen gravitational force. We had seen how gravitational force come into the picture in case of question that we are going to solve. Gravitational force will come in the form of weight, and it will be always acting vertically downwards. Yes or no? We remember this, everyone? Okay.
Yes, sir.
The second type of force, and I told you that whatever forces we see around you, around us, are either gravitational force or they are electromagnetic forces, and we are supposed to do the first type of force. Do we remember this? The first type of electromagnetic force that we are supposed to know, we may call it as the contact force or the reaction force. Now, this word reaction force might be a bit confusing, so we may call it better as the contact force. Now, what is this contact force? Whenever two bodies are kept in contact, for example, this is the floor or ground, and this is a body kept on floor or ground. And let us assume that this body is moving with a velocity v. Now, whenever two bodies are kept in contact because of interaction between their molecules, atoms, or whatever you call them, they will exert forces on each other. That force is known as the contact force, or you can call it the reaction force. Now, how does this reaction force, in what direction does this reaction force come? In this case, it may come in this direction. We call it R, the reaction force. Let me not draw it this way. Let me draw it from the center. So it may come like this in this particular direction, R. This R is the force exerted by this floor on the body of mass M. So this R is the force exerted by the ground on the block M. Now here we have seen Newton's first law of motion, but here we might use the third law of motion as well. And that third law of motion, anyone knows that third law of motion?
And for every action, there is an opposite and equal reaction, sir.
For every action, there is an equal and opposite reaction. So if the ground exerts a force R on this block will also exert an equal and opposite force on the ground. So this is the reaction force that the block exerts on the ground, but normally no one is asking us to find the force on the ground, and therefore we do not draw it. But we must understand that this R, the down wala R, is the reaction force exerted by the block on ground. Let me just discount it. So let's forget about this. So this R is the force exerted by this ground on this body of mass M. We call this as the reaction force. So what do we mean by reaction force? Whenever two bodies are in contact with each other, they exert forces on each other. That force is known as the reaction force or contact force. That force is known as the reaction force, or you can also call it as the contact force. And this is given by this R. In the diagram, I have mentioned it as this are the reaction force. That's all that we need to know. Now, since this is a force which can go in any particular direction, we can resolve this force into two components. One of these components is going to be perpendicular to the two bodies, and one of the component is going to be parallel between the two bodies. So this force can be resolved into two components, one which is perpendicular to the body, the other which is parallel to the two bodies. What is this perpendicular component known as?
Normal reaction.
Yes, this perpendicular component is known as the normal reaction force. Normal RF, normal reaction force. And what is this parallel component known as?
Force.
Yes?
Frictional force.
Yes, this normal component is known as normal reaction force, whereas this parallel component is known as the frictional force or friction. So this reaction force can be divided, can be resolved. R can be resolved into two components. N, the component which is perpendicular to the bodies, and it is known as the normal reaction force because it is perpendicular or normal. And then you have F, which is parallel to the two bodies. So that is the major force that we are going to study in this class, the normal reaction force and the friction force. Right now, if friction is neglected, and in the beginning we will neglect friction, if friction is neglected, then this reaction force does not have any parallel component, and this reaction force becomes equal to the normal reaction force. Do we understand this? So for time being, we are going to neglect this frictional component. This friction component will come in the next topic, friction. If we neglect this frictional component, so this reaction force which was going at this angle does not go at this angle. Now it becomes normal reaction force. So right now what will be concerned would be the only normal component of this reaction force, which will be known as the normal reaction force. Do we understand this? Now, this normal reaction force will always come whenever two bodies are in contact. For example, if a body is kept on a inclined surface like this, and if I ask in what direction the normal component, the normal reaction force will be, the answer is very simple. The normal reaction force will be normal to the two bodies, and it would be like this. Do we understand this? Whereas the weight, if you draw, would be coming like this in the vertically downward direction. Do we understand this? Now, this normal reaction force will always come whenever two bodies are in contact. So, for example, if I have more than one body here like this, if I have, let us say, two bodies, this body is M1 and this body is M2. And then if I ask what will be the contact forces on these two bodies, so what are the contact forces that you will see on these two bodies? One contact force on these two bodies would be coming from the ground. So you can see N1 and N2. Do we understand N1 and N2?
Yes,
This
sir.
N1 and N2 is coming because of what? The force from the ground. It's coming because of force from the ground. Are there any more contact forces between these two bodies now? or there's only one which is coming
One,
from
sir.
ground? Hmm?
Sir, one, sir. One, sir.
One more, sir. Which one, sir?
One, sir. One, sir.
I can't hear you. I'm not able to understand what you're saying. So N1 and N2, these are the two forces that I've drawn that is coming from ground. Am I asking? I'm asking here. Is there any other contact force that you see that will come? Yes or no? Yes. Then from where this contact force is emerging and on which bodies is this contact force going to act on? As you can see here, there is a contact between mass M1 and M2 as well. And because of this contact, M1 and M2 will also exert forces on each other. M2 would be pushing M1 like this, and M1 would be pushing M2 like this. Yes or no? So there will be one more force which will come on M1 and M2 because of contact. If I call this force as R, which is the contact force applied by M2 on M1, M1 will apply the same force but in the opposite direction. So this R is the contact force coming because of contact between M1 and M2. Do we understand this? And here also we are neglecting any friction between the two blocks. Therefore, we are only drawing the force which is normal to the two bodies. This is what we understand by contact force. Everyone understands this? Yes or no? So whenever you see a contact between two bodies, there will be a contact force coming there, no matter what the body is, no matter what it is in contact with. For example, if you have two vertical walls like this, and you have a rod or a ladder kept like this on these two vertical walls. Now, this ladder is touching the vertical walls at two positions. So there will be normal contact force coming. If I call this normal contact force as N1, it is because of the normal contact with ground. Then there will be a normal contact force N2 like this because of contact with the wall on the vertical side. Do we understand this? So this is your normal reaction or normal contact force. It comes because of contact. Wherever there is contact, you will have this normal contact force or normal reaction force. So that is the second type of force that we have seen, the contact force or the reaction force. Now there is one more force that will come in many questions that we are going to do, and that would be again a type of electromagnetic force. So this is the second type of electromagnetic force that we are going to see, and what it is known as? It is known as tension. It is known as tension. How does this tension come? Whenever you have a block, whenever you have a block attached to a string, when I say string, string is nothing but a thread, a wire, a very thin wire, rope, all these things are known as strings. So whenever a block is attached to a string or a wire, there is a force that comes in the wire. Now, why this force comes? It is because of the interaction between the wire and the block. Their molecules, their atoms are interacting with each other, and those interactions are electromagnetic in nature, and therefore comes the tension T. Now, again, this tension T would be an action reaction force. Whatever tension or whatever force rope is applying on the block will also apply on the rope. Now, if I ask you from this diagram, what will be the direction of force? This tension force applied by the string on the block. What will be the direction of the force applied by the string on the block? In what direction string will apply force on the block? It is hanging like this vertically. In what direction will the string apply force on the block? Upward, downward, leftward, rightward, or like this? Upward. It will apply a force upwards. Since it is tension, so we call it T. Now this is the force applied by the string on the block. No one will ask you the force applied by block on the string, but if someone asks you what is the force applied by block on the string, it will be the opposite of this. And this T that I have drawn downwards, it is the force applied by block on the string. No one is going to ask you this. So let me take this off. So this is the force T applied by string on the block. The string is also pulling the ceiling. What is the force applied by string on the ceiling? In which direction? It is also attached to the ceiling there. It is also trying to apply a force on the ceiling. In what direction is it applying the force on the ceiling on which it is attached?
Downwards.
Downwards. Now, when you see this, that it will apply force on the ceiling downwards, you can understand one thing, that string or tension in the string can only pull things. You cannot push things with a string. So that is what you must remember about a string. The first point that you must remember about a string. Tension in a string can only pull. You cannot push blocks using a string. So the direction of force in the string will be such that it is pulling everything. Strings can only pull. Strings cannot push. You have to remember these small points about these strings and this tension, so that whenever we are encountered with a question, we do not get trapped. Tension can only pull. Now you can see here what I have drawn here. Both the tensions I have drawn same. The directions are opposite, but the tension is same. Now when can this tension be same and when can this tension be different? So remember, strings are considered as massless, frictionless, strings are considered, we consider them, they may be so, it may not be so, but we consider them as massless and frictionless, and also inextensible. What do I mean by inextensible? Now in practice, in practical, whenever you attach a block by a string, there is some extension in the string. The string gets, even if it is a very tough or strong string or rope, very strong, even if it's a very strong string, it will stretch somewhat. But in our consideration, what we are going to take is that the strings are going to be massless, strings are going to be frictionless, and strings are going to be inextensible. Such strings are known as ideal strings. It will not be mentioned in the question that the strings are ideal, but we will consider that strings will be ideal. There could be some case where the strings will have mass, and we will do those questions separately. There will be some case where the strings is going to have mass. We will do those questions separately. There will be no case where the string is going to be frictionless. I mean, there will be no case where friction will come on the string. Friction will come on the string only in the chapter of rotation when things start to rotate. So not right now, they will not come. Extensible strings getting extended will come in the chapter on elasticity, so we don't have to worry about this. In this chapter, the only thing that will happen is the string may have some mass. One or two questions we will do where the strings are going to have mass. Otherwise, strings are going to be massless, frictionless, and inextensible in this chapter. Do we understand this? Okay, now such string is massless, therefore we have this third statement: tension in the string is same everywhere. Why this happens? Since they are considered massless. Since they do not have any mass, the tension in the string would be same. If the string has mass, then what will happen? Suppose I make a string. Suppose I draw a diagram like this. And now I have a string which has a mass m1. I have a string which has a mass m1. If I say that the tension at this point is T, will the tension be same on the upper part of the string? The tension at the upper part of the string is not going to be same. It will be different. Why it has become different? Because the string now has a mass. Which tension would be more? The lower tension or the upper tension? Which tension would be more? The lower tension or the upper tension? Yes. Which tension do you think would be more? The lower or the upper one? The tension on the upper part will be more than this tension T in this case. In fact, when time comes, and it will come probably today, we will find out that the value of this T is going to be simply mg, and we will find out that the value of this T1 will be going to come as m1 plus m times g. So you can see that tension T1 would be different from tension T when the string gets a mass. Those questions are very few and very rare. Whenever these question comes, we will tackle them. Do we understand this? Yes or no? Okay. So strings do not extend, strings are massless, strings can only pull. This is what we have learned so far. What else? Now, in most of the cases, we will have bodies attached to the string. Now, let's take the example of bodies attached to a string. So the case would be like this. There could be a body M1 like this. There would be a body M2 like this. And I might be pulling them with a force F. Simple case. Here, as you can see, there are two strings. This is string number 1, and this is also probably a string. This is string number 2. So I'm pulling them with a string. Now again, remember that both the strings are ideal. Now if I say that This block moves forward with X. How much will block M2 move? Will it move by X or will it move by something else? It will move by the same displacement X. Yes or no? Because they are attached to the same string. They cannot move differently. Because if they move differently, that means either the string has extended or the string has become loose. Do we understand this? So they will move by the same distance. They will have same velocities and they will have same magnitude of acceleration. Do we understand this? So two bodies attached to the same string has equal magnitude of displacement, equal magnitude of velocity, and equal magnitude of acceleration. I've used this magnitude everywhere. I've used this magnitude everywhere. Why did not I say they will have same velocity, same acceleration, and same displacement? Remember, velocity, acceleration, and displacement are vector quantities. They do not have only magnitude, they also have direction. In this simple case, they are having the same magnitude, they are also moving in the same direction. Is it possible that they have the same magnitude, but they move in different directions when they are attached to a string? Can you think of a case where two blocks attached to a string, they move in different directions? Can they move in different directions? Yes or no? No. They can move. They have to move in the same direction. They are attached to a string. They have to move in the same direction. How can they move in different direction? It is not possible. Comes the next character. And the next character is known as a pulley. Comes the next character, and the next character is known as a pulley. And this is what a pulley is like. It looks like this, and it might have a rope going around it. Now, whenever someone talks about pulley, remember pulleys are treated as massless and frictionless. Whenever we come across pulleys, they will be treated as massless and frictionless. In short, they will be known as ideal pulleys. We will come across pulleys which have got mass in some questions in this chapter, but we will never come across a pulley which has got friction, because pulley which has got friction will come in the chapter on rotation. Now, what is the function of this pulley? Pulleys are a mean to change the direction of motion. Pulleys are means to change the direction of motion. That is the only reason that I would use pulleys. Change the direction of motion? How can I change the direction of motion using a pulley? Two blocks attached to each other will always move in the same direction. But if I want to make them move in a different direction, I would use a pulley. Now you see what has happened. Now I have a block M1 and I have a block M2. Now they are still attached to the same string, one string, but now this string goes over a pulley. Now if I ask you, this block, if it moves down by X, where will this block move? It is not going to move down. It is going to move forward. Yes or no? But it is attached to the same string and a string cannot extend. Therefore, if this moves down by X, this will move forward by X. The magnitudes are same, but the directions are different. Do we understand this? And that is why I used what I used. See, that is why I used this term magnitude, 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 because they can have different directions of motion, but they still have the same magnitude. Do we understand this? So pulleys are a mean to change the direction of motion. If this block moves down with velocity v, this block cannot move down. This block will move ahead with velocity v. The magnitudes are same, directions are different. Do we understand this? One more example. Normally a pulley hangs like this. You have two blocks attached like this. This is block 1, this is block 2. Now look at the same thing here. If this block moves down by X, the other block cannot move down. The other block has to move up by X. Do we understand this? Again, the direction of motion has changed. One is moving down, one is moving up. And what is the cause of this change in direction? The cause of change in this direction is because of the pulley. Pulleys are a means to change direction. Do we understand this? So whenever we see a pulley, it is because you want to change the direction of motion. Pulleys are massless, frictionless, and they are a means to change the direction of motion. I hope everyone is clear with this. Yes or no? The next point you have to understand about a pulley is pulleys are frictionless, and hence they cannot rotate. In this chapter, our pulleys are not going to rotate. They are only going to rotate in the chapter on rotation. They are just going to remain like this. So what is going to happen here? String only slips on the pulley. So string slips on the pulley and pulleys only rotate. Tension on both sides of pulley remains same. Since the pulley does not rotate, tension remains same. So for example, if I draw the tension on the pulley, the tension is T here. Remember, rope only pulls the pulley. The tension on the other side will also be T. Do we understand this? Tension remains same on both sides. This is what I mean to say by this. We understand this? Yes or no? Okay. Now, this is what we need to remember about pulleys and tension. There are also two more points. Let us discuss them as well. string always remains taut. Taut means it always remains tight. When string remains taut or tight, that means that simply means tension in the string never becomes equal to zero. Because if the tension in the string becomes equal to zero, all of the things that we have learned will not be valid. When is not taut, string becomes loose, the blocks can move according to their will. Do we understand this? Then we cannot say that this block will go down, so this block will go up, because the string is not tight. When the string breaks, when the string breaks or it becomes loose, tension becomes zero, and then the blocks are no longer attached to each other and they can move in whatever way they want to move. So, whatever questions we are going to do will be the question the string will remain taut or tight. No one is going to tell us this. The string will remain always tight. We have to assume that that is the case. Unless and until they say that the string is loose, we'll always assume that the string remains tight. So, these are the important points that you must remember about tension in a string. I hope these points are clear. String can only push. Strings are massless, frictionless, ideal. Tension in the string always remains same. If the tension is different in the different parts of the string, that means the string has mass. Two bodies attached to the same string will have same magnitude of velocity, displacement, acceleration. If you want to change the direction of motion, what do you bring? You bring a pulley, which are frictionless and massless. They do not rotate. String only slips on it, and it's a mean to change the direction of motion. Tension on both sides of the pulley will remain same, and string always remains taut or tight. It does not break unless and until someone makes a question where it breaks. These all things, do we understand this, or is there any doubt on this? Then that will bring us to the next part of this chapter, and which is the most important part from here on till the last day of your class in 12th standard, and that is known as FBD. What do you mean by FBD?
Free body diagram.
Most important aspect. If you can ever do a problem without drawing a FBD, means you are plain lucky. That problem does not exist. That can be done without drawing a free BD. What do you mean by a free BD, a FBD, or a free body diagram? Anyone can tell me? What do you mean by a free body diagram?
Some, some external forces accelerate bodies.
Some external forces are acting. Sorry? Free body diagram.
Some external forces accelerate bodies.
Some external forces are acting on the body. Sorry, I mean, your voice is not clear, but I think I'm not able to make out clearly what you are saying. Free body diagram, it comes from the definition itself. Free, it's free. Body, single body. Diagram means a diagram. So basically, it is a diagram of a body which is free. What do you mean by a free body? FBD. So basically, a free body diagram means
No point acting on it.
a diagram of the body, a diagram of the body which is isolated from the surroundings clearly showing all forces acting on it. No one is going to ask you the definition of a free body diagram. So it doesn't matter whether you know the definition or not. What actually matters is whether you can draw a free body diagram or not. What do you mean by free body diagram? This is a block kept on floor. If someone tells you draw the free body diagram, what do you draw? You draw the weight mg and you draw the normal reaction. Here we are assuming that friction is not there. This becomes the free body diagram of this body. Do we understand this? That simple as this. You have two bodies kept like this, M1 and M2, and someone asks you draw the free body diagram of M1 and M2. How will you draw it? Draw the FBD of M1 and M2.
Hello, sir. First one, you can draw
Just,
it.
you just need to isolate them. So how do I isolate them? So I will draw M1 like this. I'm just drawing the ground so that I understand that they are kept on a inclined surface. That is the only reason for me drawing the ground. So I will draw them separately, M1, M2, and then I will draw the forces on it. M1G coming from ground, normal reaction, let me call it N1 because the name of body is M1. M1 coming from ground. Here M2G coming because of gravity, gravitational force, and N2G. So this becomes a free body diagram of the two bodies. Yes or no? Have I drawn it correctly? Or have I missed something? Have I drawn the free body diagram correctly or have I missed something? Have I
Contact
drawn it?
force.
Yes, I have missed the contact force between the two bodies. So I must also draw this. So this is the contact force. I should name it differently. So contact force is R. M1 is being pushed by M2. Similarly, M2 would be pushed by M1. This becomes a free body diagram. Do we understand this? So these are simple cases of drawing free body diagrams. So I'll give you one more case, and I would hope that you can draw the free body diagram of this one. M1, M2, M3, and I apply a force F on M1. Can you draw the free body diagram of M1, M2, and M3? I'll give you 1 minute to do this. Remember, the first step of doing any question is drawing free body diagram. Have you drawn it? Okay. Shall I do it? How are you supposed to draw the free body diagram? Just be patient and careful to not make a mistake. So first I'll isolate the two bodies, three bodies. This is M1. I always draw ground whenever there is ground so that I understand that where they are kept. Okay. M1, M2 and M3. Now I draw the forces on this. One is the normal force. Oops. I am drawing the normal force downward. One is the weight, M1G coming down. One is the normal reaction. Let me call this as N1. Is it all? Is it correct? Or have I missed any force? So there is a force coming like this. I can draw it. I can draw. I can draw it like this. But I don't want to draw it like this. I keep the same direction and I draw it like this. Doesn't matter. The force was a push. I've converted into a pull, but I've kept the direction same. But remember, F1, M1 and M2 are in contact. So there is a contact force between them. M2 is pushing it back. So I call that force as R1. Do we understand this? This becomes the free body diagram of M1. Let me now move on to the free body diagram of M2. This is M2G. This is N2. Now remember this M2 is pushing M1. So M1 is also pushing M2 with the same force but in the opposite direction. Do we understand this? So that force is R1. Is there anything else that I missed? Is there any force that I missed? Then that's it. That is the free body diagram of M2. Then what about M3? M3G here, N3 here. This becomes a free body diagram of M3. Do we understand this? Yes or no? Anyone has drawn this? This is wrong. I have missed forces. M2 and M2 and M3 are also in contact. So M3 will be pushed here and M2 would be pushed here. I must also draw those forces. So here comes that force. Let me call it as R2. R2 is the force exerted by M3 on M2. Similarly, this R2 is the force exerted on M3 by M2. Do we understand this? This is how, if you forget a single force, then your entire free body diagram will not become correct. One more free body diagram before we go. This is M1, this is M2. Now, if I ask you to draw the free body diagrams of M1 and M2, how will you draw it? I'll give you 1 minute to think about it. Has anyone drawn the free body diagram? How does it look like? This M1G on this block. There is tension T on this block. This becomes the free body diagram of this block. Do we understand this? We come onto this block, M2G is here. Tension would be same because the string is same. So this green thing becomes the free body diagram of M2. Do we understand this? But sometimes we might be also interested in the free body diagram of the pulley. If I draw the free body diagram of the pulley, this would be T and this would be T. Both tensions pulling it downward. Do we understand this? Then there would be a tension T. And it cannot be T because it is a different string. So I will call it as T1, which will be trying to pull the pulley up. Do we understand this? So this becomes the free body diagram of the pulley itself. No one is going to ask you the free body diagram of pulley, but this is how you draw it. Do we understand this? Now what you got to do when you go back home is you would have a sheet. In that sheet you would have questions. You don't have to solve questions, but in those sheets there would be diagrams. Draw the free body diagrams of those blocks so that you can practice a lot of free body diagrams. Wherever you see a diagram in any book, any question in any book, just draw the free body diagram of that body. Can you do that? Try
Yes,
free
sir.
body diagrams. I will take 2 or 3 more cases of free body diagrams. Once you have drawn this free body diagram, you have solved 80 or 90% of the question. Only 5 or 10% of the question remains. You just have to make the equations. So the most important aspect of this chapter is drawing free body diagrams. Please draw free body diagrams. I'll see you in the next class tomorrow. Take care. Have a nice day. God bless you all. Bye bye.